my PDFs through Blackboard?
Your what?
My PDFs of the master sets through Blackboard.
Oh, PDFs. Yes, I did. They should be, they're graded and posted now.
I also have I was going to say, I also have the physical copies when I get back on Monday.
Yeah, I don't think I'll need them unless there's something in the physical copy that wasn't in the PDF.
Okay, thank you.
Was that for master sets 8 and 9 or 10 or 11? You said we're done.
I've graded all the master sets except what was handed in today and for the one that had no name on it.
Okay, thanks.
Sorry, it was one that I usually get loads of questions on, and I'm just assuming people haven't gotten to it yet. But it's possible that was a 151 question and not a 251 question.
Awesome.
So Monday or Tuesday, one of those days, which master sets are due? 12 and
12 and 13
okay.
are due some point.
Okay.
I write it down so I don't have to remember.
10 and 11 were last night.
10 and 11 were due yesterday.
All right, that's the problem there.
Dude, I've got like.
Oh, no, this is it. Problem number 2 from
This is all
master set
that.
13. All right. So problem number 2 here is seemingly complicated, but it's not as bad as you might think. There's just a bunch of unknowns, and so you'll need multiple equations and need to solve simultaneous equations. All right, so we have a student J makes himself as cylindrical as possible while sitting on a spinning chair.
You said what number is this?
This is problem number 2 from master set 13. So we're modeling this J as a cylinder. This actually is based upon my first year students tried to do this, and one of the students basically brought his knees up to his chest and held on, tried to become a cylinder. His center of mass is 0.1 meters away from the axis of rotation of the chair. So we got it. So there's a chair here, and axis of rotation of the chair would be here, and center of the cylinder is there. So this was 0.1 meters. I would like to think at this point you're immediately going we're going to have to use parallel axis theorem.
I'm sorry, what is 0.1 meters?
The distance between the center axis of rotation of the chair that he's on,
Okay.
and the axis of rotation of the body,
Okay.
Oh.
or the center of mass of the body.
Okay.
Okay.
So we're going to basically shift the axis of the cylinder 0.1 meters.
Oh, okay.
His mass is 65 kilograms. The cylindrical shape is making us a circumference of 1.2 meters. So I give you the circumference. I'm writing it in fading markers. There it is. So 1.2 meters.
Okay.
And I gave his mass was, I think I said 65 kilograms.
Yeah.
So the first question is, what's the student's moment of inertia about his center of mass? So you're just doing moment of inertia of a cylinder rotating about its central axis. There's a formula for it, plug and chug. The next is, what is his moment of inertia about the axis of rotation of the chair? So we got a chair here. And so parallel axis theorem, because in the end, he is not spinning about his center, he is spinning about this point, not this point. Parallel axis theorem, the moment of inertia about some axis P is equal to the moment of inertia about its center of mass, or the axis going through its center of mass, plus mh squared, where h is how far you've moved the axis. which in our case is 0.1 meters.
Wait, what is C?
This represents center of mass. So an axis that goes through the center of mass, we're shifting that axis from here to a parallel axis here.
Okay.
So this is the formula, this is the answer to part A.
That, I see.
I sub C.
I see. That's the answer to part A.
Yeah.
And I sub P is the parallel.
Correct. It's the how you, and the parallel axis theorem is how you find the moment of inertia when it's not actually spinning about, it's an axis going through the center of mass.
What is the parallel axis? That's just the offset that it is?
Yeah, because the parallel axis is because if I know if I have a cylinder here and it is rotating about that axis, and this goes through the center of mass.
Yes.
I got a formula for it, I can find it, plug and jug, no problem. If instead it's not actually spinning about that point, but spinning about a parallel axis,
Okay.
we need to adjust our formula. And you adjust the formula with this formula by taking the mass of the cylinder times that distance squared. And you add that to the other one.
I get it. Okay. So we'd adjust. That makes sense. Be fine. And that's why I like the way you do your questions. Like the first part always ends up for the second part. And if there's a third part, you use the second part for the third part.
And
Yeah, thank you for that. I don't know if you've ever, that's been underappreciated, but that'd be great.
Yeah.
But I do want to say, if you know you need part A to do part B, and you can't do part A, but you can do part B, if only you do A, make up a number for A and use it and work. Show me that you know how to do B. Don't just stop, please.
Yeah.
And I'll take off for A, but then next to B, I'll scrawl what's supposed to be the word given. It's correct given what you did before. All right. So all of that's simple enough plug and chug. The cylinder rotating about that axis, page 365 of the textbook, or just going to internet search of moment of inertia cylinder. It'll probably give you two formulas. One of it's rotating about its central axis like this, and potentially it'll give you the other one where it's rotating about that axis.
Wait, like sideways?
Yeah.
What?
I mean, if this were a cylinder, I mean, it could spin about that axis, or it could be spinning about that axis.
Oh, that's true.
Couldn't it also go like that? Like
Yeah.
taking it like that bottle on its side and spinning it?
Yes. I mean, there are, usually the simple sites will give you just the classics. I've yet to find one that doesn't give you this one. There are some more sophisticated sites which will give you around the three main axis, rotational axes. All right, so the second part is the part where there's issues. Determine the angular acceleration due to torque from friction. So friction is applying torque because as you're spinning, no spinning chair will spin forever. Eventually it will stop. So you're trying to figure out how much friction is, what the torque is from the friction. So as it spins, it's stopping because there is torque being applied to it.
Due to friction.
Due to friction. We are assuming air resistance is not of any importance. So it's spinning around, it's got an angular velocity in that direction. The torque being applied to it has to be oppose that because it's slowing down.
Right.
All right. So Jay's in first position, the cylindrical position, and John times the time it takes to go around. So as this chair is going around, timing how long it takes to make some rotations. First complete revolution while spinning takes 1.8 seconds. So that's one revolution, 1.8 seconds. We are assuming constant acceleration. And so we use the Higgs formula. Please wait. Why?
Well, it's starting to go slowly.
All right, so my cake formulas for rotation. Well, first let's just put up the other ones. I knew I would do this. Starting to get a blister on my finger from using my fingers. What is that? I know that VF equals VI plus AT. I know that VF squared equals VI squared plus 2A dot delta S. These are the formulas that you know and love. That's a squared there. Then I've got my two displacement ones. I got delta S equals VIT plus 1/2 AT squared. And delta S is equal to VI plus VF over 2 times time. All right, so we got the four classics there.
Classic.
Rotation, you just put in the rotational analog. Instead of speed, we have angular speed. Instead of acceleration, we have angular acceleration. Instead of displacement or position, we have angle. So we get omega F. Omega F is equal to omega I plus alpha T. Omega F squared equals omega I squared plus 2A dot delta theta. Delta theta is equal to omega IT plus 1/2 alpha T squared. And delta theta, with vector, is equal to omega I plus omega F over 2 times time. Time's the only thing that's the same for both, but all the rest just put in the Greek letter.
What is that thing pointing at the top?
This,
Yeah, what is that?
that was a mistake with my hand.
Oh, okay. I was very confused.
That's not the scribble you want to be looking at. All right, so this third one here is the one that's probably going to be the most important one.
Change the name.
So the clues that they give in this is that the first complete revolution, so what's the angle?
2 pi.
Thank you. 2 pi, yes, we want to use radians.
We want to use radians.
So I have 2 pi equals, well, I don't know omega I and I don't know alpha. First complete revolution takes 1.8 seconds. So I know this is omega I times 1.8 plus 1/2 alpha, 1.8 squared.
Okay, we don't.
The second bit is it tells you how long it takes to make 3 revolutions. So what would the angle be? I think I heard it, 6 pi. Is omega I times whatever that time is, 5.9 seconds. Plus 1/2 alpha, 5.9 squared. Because it was the same journey. You start spinning it, and then you time for 1 revolution, you time for 3 revolutions. The omega I is the same for both situations. Alpha is the same for both situations.
Okay.
I have 2 equations, 2 unknowns. Once I find alpha, I now can figure out, have some sense of the torque. Because I know that the torque is equal to, the total torque is equal to the moment of inertia times alpha. Well, we figured out the moment of inertia already. sorry, I apologize. We found out the moment of inertia for J. We have not found the total moment of inertia because we have the chair also spinning. So this total torque is equal to the moment of inertia of J, which you already found in part B, plus the moment of inertia of the chair, times alpha, which you calculated there. So you will have two unknowns here, chair and the torque.
Wait,
total
we know
torque.
alpha?
Pardon?
We know alpha?
Well, this
You
one
will once
just
you solve this.
calculated.
Oh. Oh, that makes sense. My bad.
So this alpha right here is answer to part C. J goes into a second position. He gets out of the chair and they spin the chair. So J then gets into second position and tests it again. John times takes 2.3 seconds and 7.2 seconds for the first 3 revolutions. All right, so the next time around, we don't know the moment of inertia of J. So why don't we call this J1, which we have calculated already. So the first position he's in a cylinder, second position he's not. I give you times again. And omega I will be different because it's now a new situation. Alpha should be the same. Just want to double check that my thinking right now is the same as it was.
Wait, what's alpha? Is alpha just acceleration but for angle?
No, alpha is different. Never mind.
Never mind.
Sorry, what was your question?
Because didn't it state at the very beginning we got constant acceleration?
Yeah, so so J sits in it, gets in a cylinder, you spin the chair, we assume angular acceleration is constant while it's during this trial.
So we can't just assume that acceleration is 0.
No, definitely not. If you solve for angular acceleration here, you'll find that it does, that it is not 0.
Okay.
If it were 0, then multiply that times 3, you'd get that. Now, I will say that I am expecting, since I made this angle positive here, I am expecting the initial angular velocity to be positive, and I expect the angular acceleration to be negative. So if you get them both the same sign, that means it's speeding up, which is not the case. All right, so he gets into the second position. John tests it. The only difference is, this is first position. Second position, we have different times. You do the same thing, the answer to part D. Then J gets out of the chair, spins the chair just by itself, calculates the angular acceleration of just the chair. Sorry, spoiled that for you. Just went ahead and gave you the angular acceleration of just the chair alone. So we have, I guess, torque total 1, torque total 2 is going to be equal to I of J2 plus I of chair times alpha 2, or alpha 1. And then we'll have torque on just the chair is equal to I chair times alpha chair, and this is given to you.
Alpha chair.
Oh, alpha chair.
So
Pretty cool chair.
It's the alpha
what is
chair.
the moment of inertia of the chair? Let's see, did I give, that shows up in just a moment.
Was it the chair the sensor, or was J the sensor?
Say it again?
was when we were looking for the moment of inertia for the sensor, was that just
I still missed the one word. The moment of inertia of the
the center?
Center.
Yeah, at the
Center.
beginning.
The moment of inertia of the center was just to start to get your mind into the game.
Okay.
But the moment of inertia of J1, that's the answer to part B. That's
Okay.
you basically take your answer to part A, shift it using parallel axis theorem, and that's this IJ1.
Okay.
Answer to part B. This will be part C. Define that. Actually, you find part C here, and you'll plug that into here. This is the answer to D. And we're trying to find I of chair. And
All right. A2.
there is an assumption that. Oh, there we go. It was near the top. This is what I was reading just now. Assume the friction is directly proportional to the weight of the chair and whatever is on the chair. Which tells us.
That Jay's not falling off the chair.
Well, yes, that is true. I hope he's not. But it tells us that that and that are the same thing.
Oh. Why?
Because both situations, Jay is sitting on the chair. So the weight of the chair or whatever's on the chair does not change between those two.
Oh, that's what I was trying to say. Okay.
Yeah. So that's when I say that the torque is just proportional to the weight of the person or weight of the chair plus whatever's on the chair.
Okay.
Make sure I get that wording right again. Or, sorry, assume the friction is directly proportional to the weight of the chair and whatever's on the chair, and the friction is what's causing the torque.
Okay.
So now we have, let's see, so from that, I have that. So another piece that I skipped over.